This is SpaceTime Series 27, Episode 61, for broadcast on the 20th of May, 2024. Coming up on SpaceTime, a spectacular solar storm stuns the world, unusual activity in Earth's magnetotail, and scanning the skies for neutrinos from deep under the sea. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
The Sun has produced its biggest solar flare in nearly 2 decades. The massive 8.7 class explosion rounded off more than a week of spectacular geomagnetic storms which pummeled the Earth and created dazzling northern and southern auroral lights powerful enough to reach mid-latitude skies normally unaccustomed to seeing such spectacles. NASA's Solar Dynamics Observatory captured the bright blast, which was the strongest solar flare since 2005 and the biggest during the Sun's current 11-year solar cycle. The event's been classified as an extreme geomagnetic storm, the first since the Halloween storms of October 2003, which caused blackouts in Sweden and damaged power infrastructure in South Africa. The solar cycle is a nearly periodic 11-year change in the Sun's activity, measured in terms of variations in the number of observed sunspots on the Sun's surface. Over the period of the solar cycle, levels of solar radiation and ejection of solar material, the number and size of sunspots, solar flares and coronal loops all exhibit a synchronized fluctuation from a period of minimum activity known as solar minimum to a period of maximum activity known as solar maxima or solar max for short, and then back to a period of minimum activity again. The Sun's magnetic field flips polarity during each solar cycle, with the star's magnetic north pole becoming south and its south pole becoming north. This flip occurs at solar max. After 2 solar cycles, the Sun's magnetic field returns to its original state, completing what's known as a Hale cycle. The current solar cycle, number 25, began back in December 2019 and appears to be happening unusually quickly, with solar max likely to occur a year earlier than expected. The good news is the powerful X8.7 class solar flare, which erupted last week, was facing away from the Earth as sunspots, which spawned it, were rotating over the Sun's western or right-hand limb. The flare was caused by a cluster of sunspots known as active region 3664. The cluster was around 17 times as wide as the planet Earth itself, and it was by far the largest and most complex solar sunspot region observed during the current cycle. Starting around May the 8th, active region 3664 sent at least 7 solar flares and coronal mass ejections racing towards the Earth, often reaching speeds of up to 1,800 kilometers per second, and they triggered the most intense geomagnetic storms or space weather events of the current solar cycle. Space weather is a sudden flood of energy and ionized particles, such as protons, electrons, and atomic nuclei, triggered by powerful eruptions of solar flares and coronal mass ejections on the Sun's surface. Solar flares are explosions of energy caused by the sudden snapping of tangled and twisted magnetic field lines. These are known as flux ropes, and they emanate from sunspots on the solar surface. Sunspots are cooler regions on the Sun's surface that appear darker than surrounding areas. That's because the magnetic field lines reaching out into space from deep inside the Sun at these places prevent some of the heat from within the Sun from reaching the surface. Sunspots usually appear in pairs of opposite magnetic polarity. Their number varies according to the 11-year solar cycle. There are very few and sometimes none at all during solar minimum, and they reach a crescendo at solar max. Individual sunspots or groups of sunspots can last anywhere from a few days to several months, but they all eventually decay. Sunspots expand and contract as they move across the surface of the Sun, with diameters ranging from 16 to 160,000 kilometers. So what's behind them? Well, different latitudes of the Sun rotate at different rates, causing these magnetic field lines to become tangled and twisted, eventually snapping and then realigning through magnetic reconnection. And that produces secondary phenomena such as coronal loops, prominences and eruptions of electromagnetic energy, which if facing the Earth can reach the planet in just 8.3 minutes. Now, if the solar flares are powerful enough, they'll also drag billions of tons of coronal plasma and embedded magnetic field frozen as flux with them, exploding out into space at speeds of up to 3,000 kilometers per second, which, if facing the Earth, will reach our planet in just 15 to 18 hours. When these geomagnetic storms reach the Earth, a flux of ionized particles slam into our planet's magnetosphere, and they're then guided by the planet's magnetic field lines through the ionosphere, a region already filled with charged particles, and then down towards the north and south magnetic poles. Now, as these charged streams of plasma travel through the Earth's upper atmosphere, they collide with oxygen and nitrogen atoms and molecules, causing them to excite and emit photons, giving off a glow and producing colourful curtain-like displays known as the northern and southern lights, the aurora borealis and aurora australis. The colours being emitted by these lights depends on which particles are being ionized. Reddish-brown glows are caused by the collision of particles with single oxygen atoms in the Earth's upper atmosphere, usually above 300 kilometres. Lower down, a green hue is created by single oxygen atoms down to altitudes of around 100 kilometres. The kaleidoscope then turns a whitish-yellow beige when nitrogen's mixed in with the oxygen. Aurora also exhibit a blue, red or even purple glow in the lower atmosphere caused by the excitation of molecular nitrogen below 100 kilometres. However, as well as the spectacular auroral light shows, these highly charged particles can also cause a lot of damage, even destroying spacecraft by shorting out electronics and damaging circuits. They also cause the Earth's atmosphere to expand and contract, wobbling like jello, and that increases atmospheric drag on orbiting spacecraft, resulting in premature orbital decay and the need to use up more fuel in order to maintain an operational orbit. Worse still, space weather increases the level of radiation exposure astronauts experience, affecting their health. On the ground, these solar storms can overload power lines, blowing transformers and causing widespread blackouts. In 1989, one such geomagnetic storm blew out a whole bunch of transformers, causing massive blackouts across eastern North America. Geomagnetic storms also affect communications and navigation satellites. But satellite operators, electrical grid managers and engineers who maintain crucial technological infrastructure say while they're still assessing the impact of this historic event, most major systems seem to have weathered the blast okay. Although New Zealand's electrical transmission services did temporarily turn off some circuits around the country to prevent equipment damage. As a precaution, NASA temporarily stopped gathering astronomical data from its Chandra X-ray observatory and stowed its instruments in order to protect them from the radiation blasts. And the agency's ISAT-2 spacecraft suddenly shut down when it experienced unexpected rotation during the storm, probably caused by increased atmospheric drag. The agency says, however, there was no threat to crew aboard the International Space Station, and Beijing says their Tiangong space station also remained operational. But concerns like that were far from the minds of the general public, with the northern and southern lights at their best and social media being flooded with stunning images. Normally restricted to polar regions and higher latitudes, the auroral light show was visible all the way south to Mexico and the Bahamas and north as far as Tasmania, Melbourne, Perth and Adelaide. Now, the cause of all this, active region 3664, has now rotated off the side of the Sun seen from Earth and entered the field of view of the European Space Agency's solar orbiter, which is in the middle of a series of dives through the Sun's outer atmosphere and will undoubtedly provide a new perspective on all the activity. And NASA's Parker Solar Probe spacecraft, which is currently at the outer part of its looping orbit around the Sun, will also be able to provide some unique data. And it doesn't end there. For two of NASA's Mars spacecraft, the solar storm provides an unprecedented opportunity to study how intense solar activity hits the red planet. NASA's Mars Atmosphere and Volatile Evolution spacecraft MAVEN monitored the geomagnetic storm's effects on the red planet's atmosphere, while the agency's Curiosity rover in Gale Crater studied those same effects from the ground. For the record, the most powerful geomagnetic storm in recorded history was the Carrington event, named after British astronomer Richard Carrington. It peaked around the 1st and 2nd of September in 1859, during what was solar cycle 10. It created strong auroral displays that were reported globally and caused sparking and even fires at multiple telegraph stations. A geomagnetic storm of that magnitude occurring today would cause widespread electrical disruptions, power blackouts and other damage due to extended outages of the electrical grid. But it's not all over yet, folks. we're getting our first glimpse of a new active sunspot region. This one's been named 3685, which is now rotating into view around the eastern or left-hand limb of the Sun. And it's already erupted in major X-class solar flares, including one X2.99 event. It certainly looks like the upcoming solar max will be really interesting. This is space-time. Still to come, unusual activity in the Earth's magnetotail, and scanning the skies for neutrinos from deep under the sea. All that and more still to come on SpaceTime. Astronomers have detected an unusual event in Earth's magnetotail, the elongated portion of the planet's magnetosphere trailing away from the Sun. The data from NASA's Magnetospheric multiscale mission spacecraft are showing fleeting disturbances in the magnetotail known as substorms that are releasing energy and triggering auroral activity. Since their launch in 2015, the 4 spacecraft have been surveying the magnetopause, the boundary between the magnetosphere and surrounding plasma. They're looking for signs of magnetic reconnection, which happens when magnetic field lines converge, break apart, and then reconnect explosively, converting magnetic energy into heat and kinetic energy. In 2017, they observed signs of magnetic reconnection in the magnetotail, but not the normal signs of a substorm that accompany reconnection, such as strong electrical currents and perturbations in the magnetic field. One of the scientists involved in the study, Andy Marshall from the Southwest Research Institute in San Antonio, Texas, says scientists want to see how the local physics observed by the probes affects the entire global magnetosphere. By comparing that event to more typical substorms, scientists are striving to improve their understanding of what causes a substorm and the relationship between substorms and magnetic reconnection. During this year-long project, scientists will compare in situ measurements of magnetic reconnection affecting local fields and particles to global magnetosphere reconstructions created by NASA's Goddard Space Flight Center using space weather computer modeling. Marshall says it's possible significant differences exist between the global magnetotail convection patterns for substorms and non-substorm tail reconnection. Researchers haven't yet looked at the movement of magnetic field lines on a global scale. So it could be that this unusual substorm was a very localized occurrence that the spacecraft just happened to be lucky enough to observe. On the other hand, if not, it could completely reshape science's understanding of the relationship between tailside magnetic reconnection and substorms. Needless to say, we'll keep you informed. This is SpaceTime. Still to come, scanning the skies for neutrinos from deep under the sea. And later in the science report, new observations have now confirmed that April 2024 was the hottest month on planet Earth ever recorded. All that and more still to come on SpaceTime. China has started construction of the Deep-Sea Neutrino Telescope in the Western Pacific. The Tropical Deep-Sea Neutrino Telescope, or TRIDENT, will search for, detect and analyze neutrinos in order to study the origins of cosmic rays and explore the extreme universe. Neutrinos are elementary subatomic particles. They're generated through radioactive decay in stars, in supernovae, in nuclear explosions, in particle accelerators, and in atomic reactors. The neutrino is so named because it's electrically neutral, and because its rest mass is so small, it was long thought to be zero. Neutrinos are the most common form of matter in the universe, and having almost no mass, they're capable of being accelerated to almost the speed of light. They come in 3 known types or flavors: electron neutrinos, muon neutrinos, and tau neutrinos, each with its own specific properties. Now, confusingly, the 3 flavors of neutrinos don't line up with the 3 mass species. It seems each of the 3 flavors is made up of a quantum mixture of the 3 mass species. So, for example, a particular tau neutrino would have bits of all 3 mass species in it. Now, those different mass species allow the neutrino to oscillate between the 3 flavors. For example, an electron neutrino produced in, let's say, a beta decay reaction could end up interacting in a distant detector as a muon or tau neutrino. Now, although they have no electrical charge, neutrinos do have their own corresponding antimatter counterparts, identified by the opposite chirality or handedness. Neutrinos interact with other matter only through gravity and the weak nuclear force. In fact, they're so weakly interactive that several trillion are passing through you every second without you even realizing it. China's neutrino observatory is being built on a deep-sea plane some 3.5 kilometers below the surface. The detector will comprise 1,200 vertical strings or cables, each 700 meters long and spaced between 70 and 100 meters apart. Each string will carry 20 high-resolution digital optical detector modules. Spanning around 4 kilometers and covering some 12 square kilometers, the array will monitor around 8 cubic kilometers of seawater, looking for high-energy neutrino interactions. It'll be the fourth neutrino array of this type. The others include the famous IceCube Observatory on Antarctica, which is the world's leading neutrino telescope, the Baikal GVD Observatory on Lake Baikal, and the Cubic Kilometer Neutrino Telescope, or KM3-NET, located some 3.5 kilometers below the surface in the Mediterranean Sea at 3 locations off the coast of Sicily, France and Greece. The Cubic Kilometer Neutrino Telescope is still under construction, and it includes the astroparticle research with Cosmics in the Abyss, or ARCA telescope, which will search for neutrinos from distant astrophysical sources such as supernovae, gamma-ray bursts, and colliding stars. And the oscillation research with Cosmics in the Abyss, or ORCA telescope, which is studying neutrino properties exploiting neutrinos generated in Earth's atmosphere. Arrays of thousands of optical photomultiplier sensors will detect the faint light in the deep sea from charged particles originating from collisions between neutrinos and the Earth. The facility will also include instrumentation for Earth and sea sciences for long-term and online monitoring of the deep sea environment and of the seafloor. Once complete, the ARCA detector will form an array of more than 200 detection units. Each of these 700-meter-long cables will hold 18 modules equipped with ultra-sensitive light detectors that register the faint flashes of Cherenkov radiation generated by neutrino interactions in the pitch-black abyss of the Mediterranean Sea. The position and direction of the optical modules and the time of arrival of the light on the photomultipliers inside is recorded, and the trajectories of the particles then reconstructed from these measurements. The entire Cubic Kilometer Neutrino Telescope project should be completed and fully operational by 2026, occupying more than a cubic kilometer of water, comprising hundreds of vertical detection lines anchored to the seabed and held in place by buoys. One of the project scientists, Dr. Clancy James from Curtin University in the International Center for Radio Astronomy Research, says such a huge volume of water was required to surround the instruments because neutrinos would otherwise be extremely difficult to detect. James says the underwater telescope is bombarded by millions of different particles, but only neutrinos can pass through the Earth to reach the detector from below, so unlike normal telescopes, which look upwards into the skies, this facility looks downwards towards the Earth, thereby seeing the same skies as viewed by upwards-facing telescopes in Australia.
The particles that KM3-NET are detecting, neutrinos, they interact very rarely, and we expect KM3-NET to only detect maybe of order dozens per year. However, there's also particles from these cosmic ray interactions that hit the top of the atmosphere muons and come down. So what this means is that the detector is saturated by about 1 million muon events a day coming down from above. However, only neutrinos can actually make it up from under the detector. So the best way of saying, okay, we detected this particle, was it a neutrino or was it something else, is to look for particles coming up from underneath the detector, coming up through the Earth, at which point you can say, well, the only thing that could have possibly made it through the whole Earth to the detector was a neutrino. So what this means is that neutrino telescopes mostly look downwards through the Earth as opposed to normal telescopes when you point them up at the sky above you. And so the sky, the region of the universe that KM3-NET will be studying is the region of the universe that's visible from normal telescopes on the opposite side of the world, that is to say, Australia, which means that the sky that Australian telescopes are viewing is exactly the same sky that KM3-NET is viewing all the time. Now, neutrinos are the most common type of massive particle in the universe, particle that has mass, but they almost never interact with things. So we each have something like, 10 to the 12 passing through us every second of that order from the sun. So the neutrinos are produced in nuclear reactions. The ones we're trying to look for are produced by high-energy particle interactions going on in the universe somewhere. So I'm sure you're familiar with the Large Hadron Collider and, this atom smasher smashing together particles at, very high energies. Well, this is happening out there in the universe, but at even higher energies.
Now, the fact that it's being positioned in the Mediterranean Sea, exactly opposite where Australia is that deliberate or is that just a coincidence?
It's a coincidence. So the reason it's there is simply because it's a collaboration of European institutes, and if you want to build an instrument, it's easier to do it nearby. And the main constraint you need is to get this thing down deep, right? You need it to be deep down in the water for two reasons. One, so it's dark. So when you do sort of an estimate of the amount of light that you get detected, so what happens is a neutrino, if it does interact, will produce a burst of light, and that light is extremely faint. So you might only detect maybe a dozen photons from that collision, which is about the amount of light that you get in 1 second from my light globe here in my office that you would see in Sydney. So it's not very much light. So you need it to be in a really dark place. And you don't actually get it to be dark enough unless you're more than a kilometre under the surface of the water. The other reason is that these cosmic rays I mentioned earlier, these high-energy particles from space, they're hitting the top of our atmosphere all the time. And they produce more particles that then sort of rain down on us at sea level. And some of these particles, called muons, can actually go through kilometres of stuff. They actually don't get stopped very easily at all. And so what you want to do is shield yourself from as many of these muons as possible by going deeper and deeper. Now, you can't shield yourself from all of them, so KM3Net will detect something like 1 million of these muons a day, but nonetheless it's much easier to do at the surface. So the reason it's being built at the bottom of the Mediterranean is that there's some sufficiently deep places there to do this experiment.
Is there a reason why you've chosen liquid water rather than solid water, such as the South Pole neutrino detector, which is in
Yeah, exactly. So IceCube is the name of the instrument you're referring to. So that's the one that first discovered this sort of high energy flux of neutrinos coming from the universe. So the two reasons we've chosen water: one, it's just practical. It's there, when you're putting a large amount of money into an instrument, you have a trade-off between what's nearby and the most optimum site ever. But the main reason actually is that it turns out that water is an excellent medium to do this in, because the problem with water is that it absorbs more light than ice. So you want to detect light from these faint neutrinos, but light gets absorbed in water with a length scale of, say, 50 meters, whereas in ice, a photon might bounce around for 200 meters before it gets absorbed. However, if you ever stand on top of the snow and look into ice versus stand on top of water and look down, you see further into water, right? And this is because water doesn't scatter light as much. So what this means is when a neutrino interacts, it emits the light in a characteristic cone shape, right? It comes out with a cone with an opening angle of about 30 degrees. This is Cherenkov radiation.
That blue Cherenkov radiation light.
It's exactly the kind of light that we're detecting. This light comes from these from high-energy particles that are being, in this case, emitted by radioactivity, and KM3Net emitted from the interaction of the neutrino. And because they're going really fast through the water, they emit a shock wave, just like a supersonic jet emits a shock wave. And that shock wave comes across in blue light, whereas a supersonic jet shock wave comes across in terms of a sharp crack of sound.
There's new science to be had here.
Yes. Exactly. So the key part about KM3Net is that it's really going for a high-resolution detector. At the end of the day, it's going to act like a telescope. You're going to detect neutrinos. You get some idea of how much energy they have, but you want to find out where they're coming from, right? This is a big mystery we're trying to solve. What's producing these high-energy neutrinos in the universe? There's a lot of ideas, but we don't know the answer. So in astronomy, you take a telescope, you point it somewhere, and you see what you see, right? What's producing light? Oh, look, it's a star. However, the angular resolution of IceCube, it's not bad, but it's not that great. So when typically maybe of order a degree or so for the best events or thereabouts. And the universe is big, so when you point back and say, oh, there's a neutrino that came from this direction, what's there? The answer is all sorts of things, because you can't tell with enough precision where the neutrino came from. So KM3Net's going to have an angular resolution of maybe 5 to 10 times an improvement over IceCube. And the idea being that you can really detect exactly where the neutrinos are coming from and be more definite about their sources.
Better crosshairs to find your target.
Exactly.
I'm right in thinking neutrinos are the most common substance in the universe other than photons.
Well, there's also dark matter particles, but we don't really have to.
That's what I was going to come to next. And it's possible that neutrinos are, well, it's not possible. Neutrinos are also being considered as, some types of neutrinos, a species not yet actually discovered, are being considered as a possible candidate for dark matter.
Yeah, that's true. So basically there's three, let's call them normal types of neutrinos or flavors of neutrinos that are part of the standard model of particle physics. So we know that these normal neutrinos can't be dark matter. They're not a dark matter candidate. However, there's quite a few different theories of what we call, beyond the standard model of particle physics. For instance, there's something called supersymmetry that predicts that for every normal particle we see, there's something called a supersymmetric partner of that particle. I won't go into the exact details of this, mostly because I am not an expert on it, and anything I say will probably be wrong. However, the supersymmetric partner of the neutrino, or neutrino, which is called, is quite likely the lightest supersymmetric particle, and therefore the easiest to detect. So one of the goals of KM3Net, so mostly what we're doing is detecting high-energy astrophysical neutrinos from these sources that a detector called the ARCA detector will be detecting. There's another component to KM3Net, which is called ORCA, which will be a similar number of photon detectors, but compacted into a smaller volume. What that's going to be doing is studying a neutrino oscillation. So let's say a neutrino starts as a muon neutrino, it will travel a certain distance, and then it might be an electron neutrino.
Does it have to become an electron neutrino, or can it go from a muon to a tau, and then from a tau to an electron, or does it have to do it in a certain sequence? Or
they don't have to do a certain sequence. So however, there's a certain probability. Yeah. So there's something called a mixing matrix, which tells you how one neutrino that's created with a certain flavor and then has a certain energy, what the probability of it is to mix into the other neutrino flavors. And this is dependent upon how far it travels and what its energy is and what its initial flavor is. One thing that's worthwhile noting, though, is that we know there's the three flavors of neutrinos, but we don't know what the heaviest ones are, right? This is something called the neutrino mass hierarchy problem. We actually don't know what the heaviest and what the lightest kind of neutrinos are. So we know the differences in their masses, but of course, if I tell you that the difference between object A and object B is 5 kilograms, you don't know if A or B is heavier, right? You just know the difference.
Yeah.
And we know these differences from neutrino oscillations. So, and there's something called the normal hierarchy or the inverted hierarchy, which gives you two different possible orderings of the masses. So this is something that KM3Net's going to try to resolve through this in this much denser detector called ORCA. And that's going to be studying neutrinos at lower energies. It's actually studying the neutrinos that are produced by the cosmic rays hitting the atmosphere. And it's going to try to work out the mass ordering, weighing the masses of the most common particle in the standard model. I'd say most common, technically photons, I think, are more common, but
yeah.
So this is the other goal of KM3Net. These are the two key science goals of it. The lower energy, what we call atmospheric neutrinos, because they come from the cosmic ray interactions with neutrinos in the atmosphere, and using these neutrinos to understand the mass ordering of neutrinos. And it's that measurement that may turn up something that isn't consistent with the standard model of particle physics, right? It's possible we could get hints of a dark matter candidate there. And then the other aspect is looking at the high energy astrophysical neutrinos, where we'll be studying neutrinos from these particle collisions in the vicinity of black holes or exploding stars. And that's going to tell us about the sort of most violent and powerful processes in the universe.
One of the most fascinating things about the explosion of supernova 1987A was that the neutrinos arrived slightly before the visible light. And that's because the visible light had to travel through all the turbulence and refuse and debris of the supernova explosion itself, whereas the neutrinos, being so weakly interactive, just traveled in a straight line.
Exactly. Yeah. So it's interesting that people think of supernova as these optically bright things, but actually most of the energy in a supernova gets emitted as neutrinos. So a supernova is basically a neutrino explosion that has this tiny optical signature.
And I love that because that is exactly the right definition.
One thing worth noting is that the neutrinos that we detected from supernova 1987A and the Sun are at much lower energies than the neutrinos that KM3Net will be studying. So the lowest energy neutrinos that KM3Net will be studying are merely 1,000 times more energetic than the neutrinos we detect from the solar neutrinos, and the highest energy ones will be more like 1 million times as energetic, or perhaps even 1 billion times as energetic, actually, when I think about it.
Being so far down in the ocean, I guess you don't have to worry about things like storms and that sort of stuff. But what about the dust and or it's not dust, is it? Well, just the detritus that's floating down there at that depth. Is that a problem for the detectors?
Yes, so actually there's a whole lot of oceanographic physics, oceanographic science that I had no idea existed and now do because I'm still working with KM3NAT. So the other thing to note, by the way, is that KM3NAT had a predecessor instrument, Antares, which is still functioning, but it's only about 2% the size of what KM3NAT will be. So we know exactly how it's going to operate because of our experience with this previous instrument. So in terms of our experience with this thing, the stuff you're talking about, this detritus, one of the official names of this is Gelbstoff, so yellow stuff in German. And this is also known as marine snow. So one of the problems is that this sometimes accumulates on the top of your light detectors, right, and will block them. What you find, though, is that every now and then you get stronger undersea currents because there's still currents in the ocean even down at 2.5 kilometers. And so what you can do is you can say, well, as time goes on, more and more of this marine snow accumulates on the top of your instrument. So the light detectors that are facing upwards get a bit less sensitive and a bit less sensitive. Then there's a period where there's a higher oceanographic current. It washes the detectors clean, and then your sensitivity goes up again. And then time goes on and it slowly gets less sensitive, and then there's another high current event and it washes it clean. So you see all these sort of interesting effects in your instrument from the ocean floor. Here, one of the other interesting things you do is that you're throwing a detector into the ocean. The way it's set up is that the optical detectors are held on strings. These are very long pieces of mostly nylon cable, let's say 700 meters long. And these currents I mentioned will cause these strings to sway in the ocean. Now, when you detect this light signature of a neutrino, you need to know where your detectors were when they detected it so you can reconstruct the direction the neutrino came from. So what you do is you use acoustic pingers and sensors. So you have some pingers that go ping from known locations on the seabed, and then you have detectors which will listen for this, and then you can measure by measuring the distances from the pinger to the acoustic receiver, you can find out, where your instrument is. So, okay, that's a technical detail. The cool thing about this is that it means you hear everything else going on in the ocean, such as, for instance, whale song.
Shrimp
yes.
doing
so you can actually use this you can use this detector to track sperm whales. And because you've got an array of many of these receivers, there's actually ocean science groups that use the data from what to me is just a calibration instrument to actually track the feeding patterns of sperm whales and see, what times a day they're feeding. Because these things can dive down almost 1 kilometer or more deep into the ocean. It's amazing. So I think it might be even 1.5 kilometers or so to huge depth. And what they do is when they're hunting squid, they have a sonar that pings off the front of the whale. And then you can also see this ping go forward that you can detect. You also get a reflection off the back of the whale's skull. So by measuring the time between the initial sort of whale ping, if you like, and the reflection, you can get an estimate for the size of the whale. So there's all sorts of fascinating studies you could do.
That's Dr. Clancy James from Curtin University and the International Centre for Radio Astronomy Research. This is Space Time. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. New observations have confirmed that April 2024 was the hottest month on record and the 11th consecutive month of record heat. The European Union's Copernicus Climate Change Service made the observations based on both surface and satellite data, which confirmed that April 2024 was globally warmer than any previous April dating back to 1940. It was also 1.58 degrees Celsius warmer than the estimated average for pre-industrial levels. It follows a string of record hot months, starting from the hottest June on record last year. Global warming's added 1.25 degrees Celsius to global average temperatures since pre-industrial times, and the El Niño added an additional quarter of a degree on top of that. Overall, the data shows that planet Earth is warming by roughly 0.25 degrees Celsius per decade. That's up from the way it was warming 25 years ago, when it was more like 0.2 degrees Celsius per decade. Meanwhile, scientists say the summer of 2023 was overall the warmest in the Northern Hemisphere's tropical regions for the past 2,000 years. A report in the journal Nature reconstructed the past 2,000 years of land temperature data based on tree rings and combined this with observational measurements of more recent temperature records. They found that the summer of 2023 exceeded pre-instrumental average temperatures for the years 1 to 1890 CE by 2.2 degrees Celsius and was 2.07 degrees Celsius higher in the summer of 2023 than instrumental averages between 1850 and 1900 CE. A new study based on 20 years of research has now confirmed beyond any reasonable doubt that plant-based foods are better for your health than a meat-based diet. The findings, reported in the journal PLOS ONE, found that vegetarian and vegan diets are better than meaty ones for your heart health and chances of avoiding cancer. The research is based on 48 individual studies, all of which were conducted since the year 2000. They found that overall, vegetarian and vegan diets were strongly linked with reduced risks of heart disease, type 2 diabetes, cancer, and premature death. That's because it results in improvements in blood pressure and blood sugar management and lower body mass index. Primary plant-based diets were linked with reduced risk of heart disease caused by arteries narrowing, gastrointestinal and prostate cancer, and dying early from heart disease. However, in pregnant women, they found no benefits of plant-based diets in curbing gastrointestinal diabetes or high blood pressure. A new study claims that males with low levels of testosterone may have an increased risk of dying prematurely. The findings, reported in the Journal of the Annals of Internal Medicine, follow an investigation looking at the relationship between testosterone and other sex hormone levels together with health in aging men. The authors reviewed the results of 11 previous studies measuring the sex hormones of a total of 24,000 men using the same technique, all following up with participants for at least 5 years. When they reanalyzed all the data together, the researchers found men with low levels of testosterone concentrations had a higher risk of dying from any cause, and men with very low testosterone concentrations had a higher risk of dying due to heart problems. There's been yet another call for an investigation into the authenticity of the Shroud of Turin. The shroud is believed by some to be the death shroud of Jesus Christ. But multiple scientific studies, including carbon dating, have conclusively proven that it was actually created in the 12th century. Tim Mendham from Australian Skeptics says it's all part of a new film which fails to provide any new evidence.
Yeah, there's a bit of an industry of documentaries on the Shroud of Turin and books on it, etc. It's an ongoing debate. Despite scientific investigations, it doesn't seem to go away. Now, Shroud of Turin is a cloth, I think everyone knows probably. It's a cloth that supposedly shows that was wrapped around Jesus after the crucifixion. And the story goes that for some reason his image was imprinted on the cloth. Okay, and the cloth is now kept in the cathedral in Turin and shown every nth number of years. So, not very often. And when it is, you get crowds coming to see it. The trouble is you can't see much, because it's actually pretty faint and vague. But if you take a photo of it and put it in negative, you actually see a lot more. Do we have negative photos anymore? I don't know. But certainly in the old days when you took a photograph, you got a negative. And that's when someone said, oh, there's a lot more detail here than we thought. And the detail includes it looked like blood from that a crown of thorns might have left or caused, not the crown itself. It looked like holes in his hands where he would have been crucified, which is not the way you were crucified at the time, but never mind, we'll leave that one for the time being. And that he has possibly broken arms, he possibly has a spear, certainly a hole in his side where the story goes that a Roman soldier speared him, which is what they used to do to kill someone off rather than just hang around there all the time being miserable. Now, this story goes that when did this shroud first appear? And the church did a bit of investigation, Catholic Church did a bit of investigation and found out it was really sort of about medieval days, 1200, something like that. And there are stories about it and some illustrations of it having been found or at least displayed and discussed around that time. There's also somewhere that there's a record of a word of warning about it, saying there's this guy foisting this shroud around as a bit of a tourist thing, a bit of a circus object, and it's a fake. Now, what it comes down to is the shroud, as we know it, a genuine object from the 1st century CE, wrapped around Jesus, and that shows him his image, etc., his whole body image, front and back, or is it something that was made up 1,000 years later for a bit of a tourist thing, a bit of a miracle cloth? There's been scientific investigations of it over and over and over again. Part of the problem was that at one stage the cloth was folded, like you make up like you'd fold a towel or a sheet, and put away, and there was a fire in the place where it was being stored, and some, I think, silver reliquaries melted onto the cloth, and where it was folded, it got burnt. So when you unfold it, you get these little burn marks of various places around the whole shroud. And they're suggesting that that might have impacted on the image. Certainly you can still see the image, but you can see there's burn bits pretty clearly. But scientific tests X-ray, carbon dating, which is not crash after this sort of thing, but, looking at the cloth itself, looking at any herbal or, seeds or any residue in the cloth, looking at the historical record, where it's been, etc. I think it first appeared in France somewhere. A group called the Shroud of Turin Research Project had a lot of people involved. Some people have complained that it had dozens of people involved, physicists and chemists and all sorts of people.
This is the one where they took samples to different universities?
That's right, to at least 3 different universities, I think, to try and get carbon dating, and they all came back the same, or pretty close to each other, as much as you can get an accuracy of carbon dating for something that old, and they all came back with it being about 1200s, roughly around there, suggesting that the shroud is not an ancient bit of material that would have been around at the time of Jesus. It is a bit of material that was woven in 1200s, and therefore the suggestion therefore was the image dates from the same time. So that was the agreement that came out of there. Now people are saying, oh, well, we can't trust them. Someone is suggesting in a recent article, a recent documentary that's coming out about the shroud, that you can't trust because some of the scientists were agnostics. And you think, well, some of them were scientists. I mean, which one do you only trust?
One would sort of hope they were agnostic.
You'd hope they were, yeah. You'd hope you get a mixture, right, of some people who were agnostic.
You want someone who's not going to be biased in their reporting, in where they carry out their study.
That's exactly right. And this documentary thinks only an agnostic would be biased against the shroud. Obviously, those who are religious people are not going to be biased.
They wouldn't care. An agnostic wouldn't care. That's
right. Well, they might. It might be a bit sort of antagonistic to it, but really, if you're agnostic rather than atheist, say.
Exactly.
It should be more
not an agnostic.
Should be more equanimity. But anyway, this has been going on and on and on for ages, and supposedly finding new evidence. These keep popping up. There's been others that have been investigating it over the years for various things, and some came back saying, oh, it is a real cloth, or but the image is not new. It's not as old as the cloth, or that the cloth is not ancient, it's 1,000 years old, etc., etc. And it's a messy area, especially if the church doesn't really like putting it out for everybody and their dog coming and taking a snip of it.
Now, look, I tell you what, if it was real, it'd be a pretty weird-looking person to start with, wouldn't he?
Yes, it's a very elongated image. The arms, the forearms in particular, look too long. The way it's sort of draped doesn't almost... there's 2 aspects. Some say someone created a statue or a carving of a man lying down, put a cloth over it, did a rubbing, as you can do on church tombs and that sort of stuff, did a rubbing with some sort of material, with some sort of chemical, and did it both sides, turned him over, flipped him over, put the shroud. The shroud is in one long piece that goes from the head down to the toes and then back up again, up the back. So the suggestion is that he was using a carving or an actual person who didn't mind sitting there and being messed around with. And so therefore some of the elongation and some of the weird things are because of the distortion from the way the cloth was draped over the person or the statue. Others would say that because the image on the cloth is supposedly a discharge when Jesus was resurrected, which is the suggestion that it was, zap, and suddenly get this image implanted on the cloth, that should have been more accurate as to a physical person. I mentioned before about the holes in the hands. People who are crucified would normally, and crucifixion was fairly common in those days. You see Spartacus, everyone gets crucified at the end of Spartacus. It's a fairly common punishment.
I'm Spartacus. No, I'm Spartacus. No, I'm Spartacus, and so's my wife.
The crucifixion, you'd normally be tied up, rope around your arms and tied to a cross. That's a nailing someone to a cross. That was certainly not common, I don't think. But if you're going to nail someone to a cross, you have to do it through the wrist. If you do it through the hand, the palm of the hand, unfortunately, it tears straight through between your fingers, or you pulls off. That'd be a nasty bit because your weight is leaning forward, and your hand pulls straight. The nail goes straight through your hand, or it comes out between the fingers, etc. That's even nastier. You put it through the wrist, and the nail can't move because it's stopped by the hand bones. All right, so the wrist is a better place. If you're going to nail someone to a cross, you do it through the wrist. As for nailing their feet, half the time their feet was on a platform, other times there wasn't. The way you died generally was that you suffocated because your arms are up, and don't try hanging up on your arms for too long. It's not good for your chest, not good for your lungs. And therefore, after a few hours, the person might be sort of suffering, and which is when the soldier comes along and sticks a spear in your side to basically hurry things along. Now, Jesus was supposed to be up there for a long time. They took him down alive, buried him in a cave, roll the rock, unroll the rock, he's not there, etc. But the shroud still was. So this is a story that's been going on for a long, long time. It's interesting, it's romantic, but apparently scientifically it doesn't hold up that well. But for the religious people, they believe it.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday, and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.